Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Dokpo Jr., your math tutor and an instructor of mathematics at the University of Liberia. So in my today's lesson, I'll be looking at a continuation lesson of our previous lessons. So when you check our previous videos, we've been discussing ordinary differential equations, how to solve ordinary differential equations. So we dealt with variable separable method in the past lecture. And we want to look at a form of a differential equation wherein we can apply some substitution when we notice that differential equation cannot be, the variables cannot be separated actually. So we said equations of the form dy by dx equals to ax plus by plus c. So if you look at this equation, it is difficult to easily separate the variables. If you have, for instance, dy by dx is equals to 2x plus 3y plus 5, for example, it's difficult for you to easily separate the variables x and y and integrate both sides to find the general solution. So in that case, we want to introduce a kind of substitution that is going to help us to easily reduce these forms of differential equations into variables separable methods. So considering that this is the general form of what we want to look at, let's substitute what is within here with some other variables. So we can say let ax plus by plus c equals to some variable, say z for instance, or t, or whatever variable you want to use. Now, because we've brought in a new variable z, remember when you are differentiating this, you are differentiating z with respect to the variable x. So x is the only variable that is referred to as the independent variable. So z and y are dependent variable, right? So we have an equation in two variables, y and z. So we find its derivative, we differentiate both sides. The derivative of ax is just like saying 2x, so it's just equals to a, plus the derivative of by is just equals to b as well. But since we differentiated a function, because we said we have y and z to be functions, since we've differentiated a function, we must attach some dy by dx, that is the derivative of the function y with respect to the derivative of the function x. So we have b times dy by dx. Now the derivative of a constant is equal to 0, equals the derivative of z is just 1, but since we've differentiated a function z, so we must attach dz with respect to the independent variable x, so dx. Now, the next thing we need to do is to solve for dy by dx so that we replace what we've gotten for dy by dx, because we are now changing the variable now from dy by dx to dz by dx. So we can have b dy by dx is equals to dz by dx minus a. So we want to get rid of this b. What we can do is that we can multiply all sides by 1 over b, because 1 over b times this b and b will cancel. You left with dy by dx. And then 1 over b times this will just give us the same thing. So what we can do is that we can say 1 over b times dz over dx minus a. So we have now solved for dy by dx. So we replace now. Whenever we see dy by dx, we replace it with 1 over b. So there's the expression now we are writing. 1 over b times dz dx minus a equals f of this. So what is this? What is this? This entire thing here is just z, right? So this entire expression is z. So it's f of z. So now what we need to do is to find the z by the x. So what we can do first is if we multiply, we cross multiply this b times this, right? So we're going to get the z by the x minus a equals. So this b times this will give us b f of z. What do we do next? We send this a across. So we have the z all over the x is equals to b, right? Or we can decide to say a plus b f of z. Now we have this entire expression now in one variable called z, right? So we can cross multiply. You have the z equals, we cross multiply, right? A plus b f of z times dx. So we want to solve for the, we want this side to be an expression only in x. But since we have z here, so it means we must divide both sides by a plus b f of z. And then we divide this side by a plus b f of z. So this cancels this one. So you will have the z now all over. Now you can decide to say b f of z plus a, whatever the case might be, and then dx. So you've seen that we have separated the variables. On this side, we have all x, so we can integrate. And then on this side, we have all z, we can integrate. So this is how we are going to reduce equations of these forms into variable separable forms. So let's solve one problem so that you see. So we have example 1, x plus y raised to the second power dy by dx is equals to a squared. Again, if we expand what is in here, like say x plus y times x plus y, we're going to get x squared, right, plus 2xy plus y squared dy by dx. So if whatever way you're going to play with this thing, it's going to be very, very difficult for you to transform this differential equations into variable separable method. So based upon the fact that we cannot easily separate the variables, so we bring in a substitution that will allow us to easily separate the variables. So in here we have two separate variables. We don't need two separate variables here. We need just one variable. So we can say let x plus y be equal to that single variable. So we can say let x plus y equals to z. So we follow the same format we just did. We differentiate both sides, considering that y and z are two functions. So the derivative of x is just 1, plus the derivative of y is also 1. But since we are differentiating our function, we must attach dy by dx. The derivative of z is also 1, but again, we must attach the z by dx. What do we do? The next step is for us to solve for dy by dx so that we replace. So dy by dx is just equal to dz over dx. Now we send this one across, it becomes minus 1. So this is our dy by dx. Now, right here now, we're going to replace this. So we have x plus y now is just equal to z. So this is z squared. dy by dx is what? dz dy minus 1. So this is times dz by dx minus 1. What else? Equals a squared. So it's just very, very simple, right? Now, our objective now is to separate the variables so that we can be able to differentiate or to integrate both sides and find a general solution. So we multiply, right? So we have z squared dz by dx minus z squared all equals to what? A squared. Now we can have z squared dz over dx equals a squared plus z squared. So what do? We cross multiply dx times this and 1 times this. So it's z squared dz equals a squared plus z squared times dx. Now this is x, so we don't need z in there, we need only x. So we must divide both sides by a squared plus z squared. A squared plus z squared. So this we cancel this one. We're left with z squared over a squared. So you can say you can say whatever you want to say. What is z squared first? So it's a squared plus z squared dz equals dx. Now the variables have been separated. We can now integrate both sides. So we integrate this side and integrate this side. Now look here now. We can use some tricks right here, because if we will not want to use that trick, it means since the power of the numerator and the power of the denominators are the same, we must first apply long division. That is the divisor, which is z squared plus e squared, must go into z squared plus 0z plus 0. Right? That is z squared into z squared is just 1, right? 1 times z squared is z squared, and then 1 times a squared is a squared. Now, if we subtract, we have z squared minus z squared is 0, and then this is just 0, so this will just give us minus a squared. So z squared can no longer go into a squared. So now what do we have? So after we divided this by this, we got our partial quotient, right? The partial quotient, which is 1. So we say the integral of 1 dz plus the integral of the remainder. The remainder here is minus a squared divided by the divisor. The divisor is z squared plus a squared dz, all equals to dx. But so this dx, the integral of dx is just x. It's just x. But why we want to go, why is it that we want to go this long way? If we can just rewrite this as the integral of z squared plus a squared minus a squared, right? Because this is z squared, this is z squared plus a squared. So we can add a squared and we can subtract a squared. So assume this was 9 squared. We will also say 9 squared minus 9 squared. Assuming this was 32, We could say 32 minus 32. That's just the same thing. Instead of using this long division. So we could just say z squared plus a squared minus a squared divided by c squared plus a squared dz. And then this x. We can separate. So we have the integral of z squared plus a squared all over z squared plus a squared dz. We separated these terms, right? And then you say minus the integral of a squared all over z squared plus a squared dz. It's just the same. Nothing have changed. This is just the same also. So this divided by this is just 1. This is just the same. So this is the integral of 1 dz minus a squared comes outside because a is a constant. The integral of dz all over z squared plus a squared equals to x. Now the integral of 1 dz is just equals to z minus a squared. The integral of dz all over z squared plus a squared is just 1 over a, 1 over the constant. Tangent inverse of the variable over the constant, or equals to x plus some arbitrary constant c. So we can reduce this. This will cancel 1. So we have z now minus a tangent inverse of z over a equals to x plus c. So what do? We send this z across. We just simplify further. So we send this entire term across. We have z now to be a tangent inverse of z over a, or that's a plus x plus c. But what is z from the beginning? What was z? Z was x plus y. So this is x plus y equals to a tangent inverse of x plus y all over a plus x plus c. So this x that is here can cancel this x that is here, because if you send this x across, it becomes minus. The two of them go out. So we just have finally y equals a tangent inverse of x plus y all over a plus some arbitrary constant c. So instead of just killing ourselves on this problem to solve it very easily, we decided not to just go directly and start to scrap in separating the variables. So we brought in the substitution. So this is how the substitution works. We're going to solve additional problems, and you will see how easy it is to work with this kind of substitution for certain differential equations. So thanks ever so much, and see you in our next lesson.